And with me today is Bruce Serafin, our mobility segment leader for AMCO Polymers. Also, want to let you know if you have questions throughout the presentation, please log them in. And at the end of the presentations, we will answer as many of them as we can. If we don't get to your question, we'll make sure we respond via email and answer them for you after the seminar. At this time, it gives AMCO Polymers great privilege to introduce our presenters from Covestro with us today. First off is Nick Sunderland. Nick is a senior principal scientist at Covestro, supporting the development and implementation of polycarbonate resins in electrical and the electronic markets. He attained his PhD in chemistry at Penn State University and has over 22 years of experience in the plastics industry. Our next presenter is Matt Polio. Matt is a product expert with Covestro. Matt holds a bachelor's degree in chemical engineering from the University of Pittsburgh and is currently pursuing his MBA online at the University of Florida International. Matt's responsible for providing polycarbonate technical support for automotive applications, including battery packaging. And our third presenter of the day is Terry G. Davis. Terry is a principal engineer with Covestro. Terry holds a bachelor's degree in mechanical engineering from Michigan Technological University. Since entering the plastics industry 29 years ago, Terry's primary focus has been on design, engineering, and application development of plastic components for automotive, solar, LED lighting, as well as thermally conductive plastic applications. He's been involved with application development for plastic materials and batteries since 2013. Welcome to the three of you. Thank you for being with us today. And now I'd like to turn it over to Nick, Matt, and Terry for today's presentation. Nick?
Thank you, Robert. And so, yes, I'm Nick Sunderland. I'll be starting off with a general overview of Covestro. And my section, there'll be three sections today. My section will focus on the charging stations. And then Matt will take over, and then Terry. So who is Covestro? So this slide here gives you the big overview of who Covestro is. So basically about 17,000 employees throughout the globe. So it is a global company. We have production sites globally. You'll see that on an upcoming slide, and research centers globally as well. While this presentation focuses on polycarbonate-based, mostly polycarbonate-based materials, Covestro does make polyurethanes, thermoplastic urethanes, coatings, adhesives, and so forth. So sometimes all of these businesses come together to make a special product. What's a little different with Covestro is that there is a commitment to innovation and R&D. So a lot of the grades shown here that say I'll be presenting, these are newer grades. There are more recycled grades, there are bio-based grades. There are efforts we're making always to try to be more eco-friendly, to try to push the envelope. So this is what you'll be seeing in these presentations. And as shown here, our purpose, to make the world a brighter place. So when you look at the globe, we have production facilities in North America, Baytown, Texas, Newark, Ohio, and the R&D center is in Pittsburgh, where I am based. This is duplicated in Europe. So Leverkusen is the R&D center there, and there are production plants, say, in Antwerp and also in Germany. And again, duplicated in Asia, where we have an R&D center in Shanghai and production plants located a bit all over China and Thailand. So the takeaway here is if we make a product in one region, typically it is globally available. So if you're molding, if your customer is, say, North America, but you're molding in Asia, we can create this grade and have it available in all regions to trial. And typically that works out nicely. That's one thing that we try to do when creating grades is they are globally available to all the regions. What does Covestro make? So in polycarbonates, we have four lines of products. The first is called Macrolon. That is a polycarbonate. So polycarbonate can be made transparent, but by putting additives opaque, it is higher heat, it is impact resistant. So if you think of, say, acrylic, for example, they're both transparent, but Macrolon polycarbonate has higher heat, higher impact, and it can be made flame retardant easily. If you take Macrolon and you put a special copolymer, you get APEC. Now, if the heat of this is about, the melting point or deformation point is 150. Now you're up to 200 degrees Celsius with this. So applications with higher heat, you have APEC. If you take Macron and you add in ABS rubber, you get Bay Blend. The advantage of this is now with the rubber and the other additives is you get very good flow and you can get low temperature ductility. So if you take Macron and you put in a polyester, you get Macro Blend. That gives you toughness, and as well, because polyesters are very good in chemical resistance, the takeaway for Macro Blend is typically you get very good chemical resistance. So the 4 lines we'll be focusing on during this presentation. So the EV charging industry. What does Covestro bring to the table? So we have a lot of knowledge in electrical and electronics at Covestro. And this translates then to a lot of the EV world. So what I'll be presenting in terms of charging and controlling is here, but it translates to battery packaging, electric powertrain, and as well, Covestro has a lot of applications in automotive interior and exterior. You put all this together, you have a solution for the entire chain of EV vehicles, from the charging to the vehicle to the battery. So my presentation will focus on this one, and my colleagues will focus on the rest that you see here. So what are the applications in the EV charging industry? So there's the charger itself, and then you have different charging stations. So the ones at home, the little wall boxes, as I'll call them. Then you have the public chargers where you may see at work or grocery stores. And then you have the DC public chargers. We're talking more of the very high capacity chargers like the Tesla and others that can charge very quickly. Where are these applications going? So according to a report from Berg Insight, about 12 million in sales expected in 2025 in EV sales. Charging stations from 0.9 to 2.6 million in North America alone in 2025. Globally, right now, from 22 to 27 million expected in 2025 of charging points globally. So this is growing. And as it grows, it means more plastic, more materials for this growth. So what we're seeing in terms of the drivers for this, while we're confident that it's going to keep going, is there is a niceness of emission-free driving, for example. So you can charge with renewable energy if you want, solar panels, whatnot. And the fact that you have government incentives also helps. EVs are becoming more affordable. Well, with the COVID, maybe that's neutral, but they are. The prices that came out when Tesla first came out were $100,000. Now you're seeing options at the 35 or so starting. Consumer adoption is increasing globally. The charging is smart. If you have an electric company, it will automatically charge at night to save you money. It makes it easier to go with your phone, your Android or iPhone. The battery technology is getting better. And finally, the last point here is companies are working together. So startups, electrical companies, OEMs, tier ones, everyone's getting together on this. So it makes this driver for charging a lot easier. So that's why there's confidence in these numbers, because of these drivers here that we're seeing. So what are the material and design trends for charging stations? So quickly here, what we have in AC versus DC. AC is what you're going to see at home. That's what you're going to see in smaller stations. Basically, AC, you take your 110 power 240, and the car itself converts it to DC. That's what it needs. So you have onboard chargers, which, that could be plastic, potentially, that converts that. The DC basically takes that DC signal and rams it into your battery directly. That's why you can get 20 minutes, 30 minutes, whereas this can take some hours with that. So as you can imagine, if this is a lot more current, the type of plastic and the flame retardants can be different that you need. Your UL ratings may be different. This is something I'll cover. And just to go through quickly with this slide, you might have heard of level 1, level 2, and level 3 charging. And level 1 is what you'll have in your garage, or maybe if you put it just outside your home. Level 2 is what you may have at work or at the grocery store, a little faster. And level 3 is really the 20 to 30 minute charging, where it's the DC level and it gets the charging done very quickly. With all these, we believe that we have materials that covers all these needs based on our flame retardancy and electrical materials. So looking at these trends, not only do you have a charging station, but it has 4G or even 5G to communicate back to the mothership. If you're paying at a grocery store or a charging point, I should say, your credit card, it needs to communicate. And our plastics will let 4G and the faster 5G as well. You know, we have done a lot of work to show that polycarbonate can let 5G through quite easily. When you're looking at a metal to plastic replacement, that's because you can have a certain design language that metal cannot do. So we sell quite a bit of plastic in charging stations because of this. There's a certain design language or corporate language that you can have with a plastic that with metal becomes very difficult. As well, the denting of metal can lead to a cosmetic effect, according to some customers. Color. I'll show you some pictures later, but if you want high gloss or matte, depending on transparent, clear, white, difficult to do with metal unless you paint, of course, but this is something that can be molded in color and you're set. And finally, we have a good handle on global regulations for these stations and charging plugs. So next step is, here's these trends. What do we need to supply you? We need to supply something that's going to resist UV attack. Some plastics can get attacked by UV. Safety, flame retardancy, impact resistance. When you get a teenager with a baseball bat, bad things can happen. So you need a plastic that has good impact resistance. And finally, a design language, colors, something that stands out. This is what we can provide with our plastics. A quick slide on global standards. This is one of 5 slides. I'm not showing the other ones, but all these global standards just for chargers, for the charging plug itself. Every country has a system of charging of what's required. We keep on top of that. So we design our grades to meet these as best as we can. So if you have questions on that, this is where we can translate these standards with our grades, with electrical properties. So just a quick slide to show you that we keep on top of this. Where can the plastic go? So if you look at a standard charging station, the front needs to be transparent. So clear polycarbonate, display lens. You may have, this may indicate if it's charged or not, maybe a light guide, maybe something that's nice and diffused. Your housing needs to be, is it going to be electrical enclosure, flame enclosure? We have something there. Finally, you have connector housings, and there may be tests that you need to pass, but this is all the things that we can offer in terms of weatherability, impact resistance, heat, UL, and chemical resistance, should there be a need for this. So let's look at an example. You have and this is a mock-up that we did, so you need to have a nice clear front cover, and then you have a housing and brackets to mount. We have all these transparent grades here. This can be flame resistant, V0 at 3, a brand new grade here in pink, V0 at 1 millimeter with 5VA at 3 millimeter transparent. 5VA means you may not have to isolate the electrical components using something else. Here, in terms of opaque, we have just a regular 6487, which is a V0 5VA grade, or we have a newer FR6020, which adds low temperature resistance down to -20. We also have R20. What does that mean? That means 20% post-consumer recycle. We have 6487RE, bio-based renewable grades. So we have options now. Should you want to have an eco options, there are eco options as well as the grades I'm showing here. So they can all be weatherable. This one, W means weatherable. They can be transparent. They can be flame retardant and at different thicknesses. The charging plug itself, we have grades. Again, the 60-20, it goes down to -20. The 60-40 goes down to -40. For example, sometimes these plugs have a rollover test if your car rolls over it. So maybe there has to be low temperature impact. And FR 6011 is a flame retardant macrolon that has good chemical resistance, brand new. You may be able to avoid a macro blend. And because we have a thermoplastic urethane business, if you want something soft touch, so there's a good grip, you can overmold this, maybe in the same tool, with a soft touch thermoplastic urethane. Options here. I talked about a corporate design, corporate language. Here is a picture of what you can have with a translucent polycarbonate. Instead of having opaque, here we have a diffused and a light guide around it. And we have diffusion grades that do that, different diffusion levels, and you can have your transparent lens as well, as I've shown before. This just gives you ideas of how you can make this different as opposed to a big black metal box. So if you want to have a certain feature that has light that shows you when it's charged, but has a soft touch glow, here's something that can be done with it to give you ideas. And these diffusion grades, and it can also be flame retardant, V0 down to 0.8 millimeters, can offer that as well. So some options to think, I can make this different with different cosmetics. I can make it frosted. I can make it diffused in that sense, a nice soft touch. So these are all possibilities with these grades. So at the end, there are different customers that we have. EV Box is one of them, using our plastics, and the housing here is what we're talking about. They could have something that gives, instead of a big black metal box, something that may light up. The rings here, you have a clear display screen, and the housing itself basically can be flame retardant and impact resistance because it's plastic. Charge point, same thing. A clear polycarbonate screen, impact resistant, with a black or gray, depending what you need, impact resistant top and housing that is flame retardant as well with a V0 5VA rating. With all these, you meet the customer requirements with as an electrical enclosure or a flame enclosure as well, because it's polycarbonate, as having the impact resistance. So in conclusion, for my piece with charging stations, where do we see EV charging go? Well, there is a pull. There's a pull because of government incentives and regulations. So that's what we see growth. There's also technical innovations as well happening with it. People are investing in this. They're seeing there's opportunities for that. So that's why we believe that this growth from 0.9 to 2.3 million charging stations will happen. We have material solutions that are EV ready. We have new flame retardant grades that go thin, and we have new low temperature impact grades as well. If you want, we can have post-consumer and bio-based grades. Design freedom. Terry is an engineer. He can talk all day about how to design this, how to give you features that you want. And finally, because we're global, because we've been working in the automotive space, the electrical space, the electronic space for decades, we can be a reliable partner for you. So I'll let you digest this. And while you look at these 4 points, that ends my piece of the presentation. I'll pass it on to my colleague, Matt.
All right, thank you very much, Nick. My name is Matt Pulio, and I am a product expert for our mobility space here at Covestro. And my portion today is going to be about helping you with material selection for electric vehicle battery packaging. So we'll get a lot of questions from injection molders and customers who have an application, they have requirements, but they don't know what material to use. And that's what we at Covestro can help you with. So starting with a few packaging components here, some areas that we've identified where polycarbonate is suitable are first in the battery cell holders. So these holders need something that is dimensionally stable, also has some impact resistance to it, and of course has a flame retardancy. But then we also see battery cells designed into these frames and tabular formats here. So there's going to be some different requirements from the frames compared to the cell holders. Additionally, we find an area for polycarbonates and cooling solutions as well. So whenever you're charging an electric vehicle battery, it often gets very hot because you want to be able to charge quickly. That way you're not standing at the charging station for 3 hours. So with the battery getting hot, we need to introduce some type of way of cooling the battery. And that's where polycarbonate can be used as a solution for the cooling systems. Of course, for something as important as the battery, you need to have some type of crash absorber. So you want to have something with excellent impact strength. And some other areas that we see polycarbonate used are in top covers, which are very large parts. And then a newer area is in light electric vehicle packs, which are smaller packs that you might see for vehicles like motorized scooters or electric bikes. So all of these has use for polycarbonates. And so we're going to look into each one to see the requirements and the materials that we recommend. But first, we'll take a view at the entire resin space for electric vehicle battery packaging. And as you can see on the left here, we have polycarbonate and polycarbonate blends. Some other materials that work well are glass-filled and thermally conductive versions of polycarbonate. Polyamide is used a lot. This is better known as nylon, and we often see their glass-filled and thermally conductive versions as well. PBT, or polybutyl terephthalate, is actually the polymer that we mix with our polycarbonate in order to make our macro blend product. And so we'll see some examples of PBT as well as their glass-filled and thermally conductive grades as well. And the last material that we'll often see in this space is modified polyphenylene ether. And again, the glass-filled and thermally conductive areas there. But when we look at the requirements for EVBPs, we see that we need materials that are dimensionally stable. So whenever you make the material hot or cold, it doesn't warp on you. We often need good impact resistance, obviously, so the battery doesn't get damaged. Temperature resistance to heat, hydrolytic stability, so when it comes in contact with water, it doesn't deform. And of course, we often want to see flame retardancy based on a UL94 rating of V0 at 1.5 millimeters. So as you can see in this chart, right, we kind of identify where some of these materials either pass or fail these criteria. So if we eliminate some of the ones that don't do very well, we're really left with about 6 materials left to choose from for EVBPs. But more recently, some more requirements have been coming out where our customers need materials that process well, have good dimensional accuracy, and whenever adhesives are used to put the pieces of the battery package together, we often want to UV cure these for quick cure. And so looking at all the materials in this space, really the only product line that meets all these requirements are polycarbonates and our polycarbonate blends. So now as we go into each one of our design areas, we'll start with the cylindrical cell holders. For this application, to select the materials, we're going to look at the requirements. So we're going to need something with high flow because a higher flowing polycarbonate will help you get into all the intricate cracks and crevices required for the part. We need that UV curability, and we also want something that's very dimensionally stable. So for that, our main product we recommend is Babeblend FR3040 EV. And a secondary product, just based on whatever the requirements are, is Babeblend FR3080 EV. So as you can see here, this has a higher notched IZOD value, indicating it's a better impact material. So if impact is something that's very important, we go with this material. If it's not as important, we stick with 3040 EV. Next up, for our pouch cells, frames, and tabs, this is one where we need the parts to be very rigid. We need to have good ductility, good impact resistance, and of course, this is another complex part, so we want to see good flow as well. So while the requirements are not as strict as the cell holder, we can go with a material like Babeblend FR3010. This is really one of our flagship Babeblend products, used in a lot of electronic equipment housings, very common grade, and we really find a home for it pretty often in EV battery packaging as well. So the next area is the liquid and air cooling systems. So these are much different systems. I would say much more complex because there's multiple ways that you can cool a battery. You can use a liquid cooling system where essentially you will transfer a cooling fluid around the batteries so it won't come in contact with the batteries. Essentially, it'll be next to the battery through a layer of polycarbonate. So if you put this coolant fluid, close to the batteries, it'll pull heat out of the battery and allow it to cool down. So those type of liquid cooling systems often require good thermal conductivity. Chemical resistance is very important because you don't want the coolant, such as ethylene glycol, to degrade your polycarbonate. Then you would just get a big mess. You need to have good dimensional stability and good hydrolytic stability as well. So for that, the material that we recommend is Macrolon FR6020. It has the chemical resistance to stand up to these coolants, and it makes for a very good heat exchange material. Now, the other way of cooling a battery, is through air cooling. So with air cooling, this is just as simple as using something like a fan to basically blow the hot air away from the battery. So in this case, you want to use a polycarbonate in contact with the batteries that can easily pull the heat out of the battery. So you want something that's very thermally conductive. In this case, we recommend our thermally conductive Macrolon, which is TC110FR. So for crash absorbers, our recommendation for this material is really the best part of our portfolio for impact resistance. And that material is Macroblend UT6007. This is a blend of polycarbonate and PBT, and it offers superior impact strength at both high and low temperatures. So for crash absorbers, this is our go-to material. All right, next up is the top covers. This is something we don't see as often, but it is a way to really give good protection to battery packages. And this is often in an application that is too large to injection mold. So for that, we need a specialty grade, and we need to use a special type of processing called long fiber transport, where basically the glass fibers are impregnated with the polycarbonate material. And you can make a big sheet that you can practically thermoform into this shape. And so our grade for that is very specialty. It's Bayblend FR3090 LFT for long fiber transport. And then the last area, again, a little bit newer. This is for light electric vehicle packs. And these are small packages used for mobility applications like electric scooters, electric bikes, smaller pieces of equipment. We could also see something like this in electronics, such as charging points for electric lawnmowers, electric weed eaters, so many different applications for something like this. And since this is a type of battery pack that will be exposed to UV, exposed to the environment, we want to pick a material that has good UV resistance. However, when you're using light electric vehicle packs, you can often drop them, right? There's a lot of handling with this, a lot of, taking it into a compartment, switching it out with another battery. So a lot of areas for it to get damaged. So you want to have good impact resistance as well. So that's where our two materials for a light electric vehicle pack are, again, our impact grade, Macroblend UT6007. But then we also have a newer grade, which is Bayblend TP2375. So this one's currently a trial product, and it was designed as a weatherable Bayblend, so it has very good weatherability, but it's also designed to have very good impact strength as well. So this is a brand new product, hasn't been commercialized yet. So if anyone on the call or anyone listening is feeling brave and would like to give this material a try, we can definitely get in contact with you about setting up some type of molding trial, and maybe you can be the pioneer of this weatherable material. So at the end of my presentation, I really wanted to touch on a little bit of, how can Covestro product experts help you? Essentially, we get questions all the time about what material would be best for a certain application. However, we can mainly use our expertise whenever we have information from you. So whenever you're contacting us or contacting your representatives from AMCO, if you can provide information on the application that you're supporting, any requirements or customer specifications, and if you can provide any information on competitive materials that you're using, so say you're using a material now and you're looking for an offset, we can help you with that. And if you're having any issues with your current materials, we can help you with troubleshooting, as well as maybe identifying a material of ours that might work a little bit better. So taking all four of these combined, that allows us to use our expertise in materials, processing, and design engineering to better help you solving your issues and helping you make the best product available. So I'd like to thank you very much for joining the seminar today and for your attention. My contact is on the slide here. I've also included the contact for our other mobility product expert, XY Lee. And now without further ado, I will turn it over to our next speaker, who is Terry Davis. And Terry will be presenting on design and engineering of some battery packaging components. So Terry, the floor is all yours.
All right, well, thank you, Matt. I appreciate that. As you can see, I'm going to take a little bit different direction than Nick and Matt have so far. So you've learned a little bit about our materials for charging stations and for battery packs. Now we're going to talk a little bit about the design with those materials. So you can pick the best materials in the world, which of course are ours, but if the design and the processing and all the things that go into actually producing a part aren't handled well, then even the best materials aren't going to give you the performance that you need. So I just want to share a little bit about that. Now, this isn't intended to be a in-depth design seminar, but it's intended to give you some ideas, let you know some of the things that you should think about, and of course, then work with us to help you design around these materials and what they need to have for the optimum performance. So when we talk about design objectives, generally speaking, the design is keyed upon the performance requirements, the abuse tests, and all the things that are going to happen to a part or an assembly or a component during its service life. So those types of things are what lead you to say, okay, how do we design a part to handle those things? And then of course, what works hand in hand is the materials as well. What material properties do we need to be able to withstand those performance and abuse requirements? And naturally, I have the design portion here very large, no offense to Nick or Matt, but this is where my area of focus is. So under design objectives, there's many things. We'll talk about a few of these just in general terms. But we need to be able to, for example, reinforce sections, give ourselves the structural properties that we need, avoid sabotaging our design with built-in stresses and problems with the design, and then, avoid problems in use like distortion due to the heat, what the environment is going to give in the service of in the part's service life. And then we talk about processing objectives. So when we actually produce the parts, when we're molding them, what can we do to help or hurt our material performance? So talking about design practices for a minute, when it comes to battery materials and battery applications, there's some good news. And that is that traditional design practices that you may be used to for plastics pretty much still apply to those parts. So there's a lot of things that are common design practices that you still need to use or can use to design parts well. You need to think about the structural requirements of the part. Am I going to have creep situations or stress relaxation? What kind of mechanical loads do I have to withstand in service? Am I designing problems into the part? Traditional issues like stress concentrators, sharp notches, all those things are still concerns with battery applications and materials in those applications. You still have to be conscious of those things. Same thing with fasteners. Am I using the proper fastener for the material? Am I using thread forming screws? Am I using thread cutting screws? Thread forming screws are generally not the best for plastic because they induce high hoop stresses into the material that they're being fitted into. So we prefer thread cutting screws. Am I supporting my bolted joints properly? Am I putting the material, am I loading the material when I tighten the bolts down? Am I doing that properly? So all these things are still issues that we need to be concerned about when we're designing. We also have some other things that happen during the design for battery material or battery parts that we have to think about. Many of the parts that we look at in batteries are thin wall. So they're, I would say, thinner than what we would call traditional plastic parts. We have a lot of people designing parts that are 1 to 1.5 millimeters thick. This tends to become pretty thin wall for a lot of plastics. And then we also see in the same light that there has to be contact with mating components. So we often find that nobody wants to use traditional draft recommendations when they're making the molds. So we see thin walls and low draft quite often in battery parts. And there's ways to handle that with material and design, but you need to be conscious of those things and consider those up front when you're actually designing the parts. Some other things, again, there's some new and not so new things that you need to think about, or I should say are related more to battery applications. For example, energy density. Energy density is a huge factor for batteries. You want to get the most kilowatt hours per kilogram that you can out of a battery design. So what does that mean? It means mass reduction. You can either increase the output of your batteries, which is more kilowatt hours, or you can reduce the weight of the assembly, which is reducing the kilograms, so you can get your kilowatt hours per kilogram higher. To do that, we can incorporate design features and get mass reduction by smart design, by creating a structure that gives you the stiffness that you need while reducing the amount of material you need to get there. So with smart design in batteries, you can get those higher energy densities and still achieve the performance requirements that you need. Another thing that's fairly common with battery applications is many people who are doing clamshells for cylindrical type cells, they will tend to use UV cured adhesives to be able to mount the cells into the holders and keep them locked in place for the assembly operations. For example, wire bonding, which is critical, obviously, to the battery's performance. You need to have the cells held rigidly and consistently in the same location for the wire bonding equipment to work properly. So many people will use UV cured adhesives to hold those cells in place. And with a lot of materials, if it's an opaque material, you can't utilize those because you can't shine a light through the opaque materials and cure the adhesives. So we have grades. We have clear polycarbonate grades, flame retardant polycarbonates, and we have a Bay Blend FR3040 EV, which all have enough UV transmission to enable UV cured adhesives to be cured through those materials. So when you make these parts, one thing you need to consider is how thick am I designing the parts? Can I get the UV light through them? And then are the parts, we'll talk about it in a few minutes, are the parts molded properly so that I don't cause myself problems with transmission? Another thing that's common in batteries is the joining of dissimilar materials. So with batteries, you have a lot of metal components, bus bars, different types of aluminum or copper pieces, and they have to be joined to plastics. And as we all know, their thermal expansion and contractions are not the same. So the metals and the plastics are very different when it comes to thermal expansion. So those joints need to be designed properly, and there's techniques to join mechanical parts mechanically together properly. And then, of course, there's adhesives that can be used as well. If a compliant adhesive is used, it allows the parts to move relative to each other, doesn't put stress on the parts and cause issues. So those joints that we have in batteries that are dissimilar materials, those have to be considered well during the design process. Of course, electrical considerations, am I getting proper creepage and clearance? And do we have the right electrical isolation in the designs as well? Matt mentioned our energy absorbing materials. We also have a design factor there as well. The materials themselves, especially the macro blends, have great energy absorbing potential, but the design is critical. The height of the features, the diameter of those crush towers that you see in this picture, and the material properties all work together to absorb the energy of impact properly and to give you your best performance. And then finally, too, there are thermal management considerations. And you'll see going forward here, we have some materials that are not only polycarbonate based, but they're thermally conductive and can help with thermal management of a battery system. So moving on a little bit to processing. When we talk about processing, we choose materials based on the performance needs, but then we have to make those parts. We have to mold these materials. So very early on, we need to look not only at the mechanical properties of the materials, but some key variables. how long is my part? How far am I going to have to push the material into the mold? How many gates can I have on that part? What is my flow length going to be? What's the wall thickness of the part? So the thinner the part, and again, some of these battery components can get very thin, and with draft, you can even be sub 1 millimeter in thickness. So how thick is my part? How far do I have to push it? And then finally, the material's viscosity. So if I want a highly structural material, especially say a glass filled material, the glass reinforced and get really high modulus from it, that generally is going to come at the penalty of high viscosity or higher viscosity. So it's going to be harder to fill the mold. So when I'm still in the design phase, I really need to look at the materials that I'm considering and think about how they're going to mold in my design. And maybe there needs to be adjustments to the design. Maybe that we need to look at a slightly different material grade. But in any case, this should be looked at up front so we don't get to the molding floor. We aren't at the first molding trial and find out, uh-oh, we can't fill this part. So talking again about processing, there are a lot of recommended standards for molding about how much material, what's your residence time in the screw and barrel and all of that. And you need to consider these things as well. Generally, battery parts are fairly good sized parts. They tend to be larger parts, especially now as battery packaging gets bigger and bigger. But you need to size them to the molding machine. Plastic materials don't like to sit in hot temperatures for very long. If your molding machine is not designed properly, if it's not spec'd properly to the size of the part, then you can end up with the material sitting in the barrels and cooking for very long periods of time. The net result is what you'll see in those lower pictures: discolorations, burned material, brown material. Those things look bad, they're cosmetic issues, but they can also give you serious performance issues as well. For example, if I'm going to try to UV cure a part through that adhesive through that part, then now I have all of that discoloration. I'm blocking my UV transmission. Another thing is I have now potentially degraded the material and lost mechanical properties. So we need to be able to, during the design process, consider the processing and make sure we're sizing everything properly for the molding equipment we're going to use. Same thing with drying. So we all probably understand that plastic materials need to be dried before molding, and this is a critical step. They tend to pick up atmospheric moisture during transport, and they need to be very dry before molding. Typically, for polycarbonate blends, you need to be at 0.02% moisture. That's a pretty low number. You need really good equipment to achieve that. And so you want to make sure that your equipment is drying the material properly to that 0.02% level. If you don't get to that level, that's when you can start to have issues. Excessive heat and moisture can cause the polymer chains to break down. That's going to affect your material properties, and then it can also give you cosmetic issues. Again, you can see we have streaks, we have issues in the part itself. Cosmetically, that looks bad, but it can also affect performance, again, if we're trying to UV cure through that material or we have other optical requirements. We also want to consider when we're molding that we don't induce stress in the parts. We talked a little bit about stress being an issue in parts. Well, it can cause all kinds of issues. Again, does it affect the transmission of the part? Does it leave a internal stress or a hidden stress in the part that comes out under loading and starts causing part failures or cracking? Residual stress can contribute to warpage. If you have a residual stress in the part, you heat the part back up a little bit, it wants to go back to its natural state. So if it's got warpage in it and you heat the part up, it's going to deform. Again, for battery applications, that's really not acceptable. The parts need to be consistent, especially for the assembly processing, and then of course in service. So we also need to consider the gate and delivery system. Again, the gate and runner system can cause many problems. It can result in high shear stress if we don't design it properly, or high shear rates in the gate, which can cause degradation of the material, cause it to start to break down. In addition to that, if say a manifold system like is shown here on the right is not properly designed or is not sized properly, we can have that long residence time or the material sitting in a very hot condition for too long, breaking down, losing properties, and ending up with a part that's not as strong as we need it to be. So even something as simple as how you get the material into the mold needs to be considered early and upfront. So from this section, what we're talking about is that Covestro has the design and expertise to support EV packaging applications. So we know how to do these things. We know how to design parts, and we know how to help process parts to make them good. What I'd like to talk now a little bit about is some of the development work that we've done to support battery packaging applications. Like Nick said, we like to learn about the applications we're in. We need to understand the market areas that we're supporting. So to do that, we will often produce what we'll call proof of concept or development components, packs, whatever you want to call them. In this case, it's a battery pack, to be able to learn a lot about these applications and also to prove out our materials in the battery arena in those applications and components. So this is a development that we did. It's a light electric vehicle pack. It's something that you might see for, say, two-wheeler or three-wheeler vehicles that you find commonly in India or Asia. But it was also designed to be flexible in that we can string several of these together in a modular form like you see in many passenger vehicles. So it's not just for light electric vehicles. It can also represent one module of several in a passenger vehicle application. And what this allows us to do is test out our materials, run them through actual cycle, discharge, charge and discharge testing, mechanical testing, and show that yes, these materials are suited for the application. So the pack that we developed, pretty common specifications for these applications. We chose the 2170 style cells. We put 110 of them in the pack, and which gives us a total mass of about 10.1 kilograms. You can see the performance specs. That's about 1,800 watt hours of energy in the pack. Very common size for these types of two-wheeler packs. And then finally, we get down to the critical component, energy density. So we're talking about 178 watt hours per kilogram, which when you look at these types of packs is pretty good performance for these packs. So if we look inside the pack, we had some components that we designed specifically out of our materials. First and foremost, the clamshells. So the clamshells hold the cylindrical cells in this case. And we looked at several different material grades, primarily Bay Blend FR3040 EV. I mentioned that earlier. That is a non-thermally conductive, flame retardant material, flame retardant PCABS. And as I mentioned, it is transparent at UV wavelengths to allow curing of UV adhesives through it. So really good choice for these types of applications. It's high flow and it will fill the thin walls very nicely. Another material, as I mentioned, for thermal management is Macrolon TC110FR. And that is a thermally conductive, flame retardant, and electrically resistant material. So it has a lot of things going on in it at one time. And this material is a good choice if you have thermal management issues and you need to be able to remove a little bit more heat from these packs. And we'll see in a moment that you do have performance, thermal performance advantages by using a thermally conductive polycarbonate versus the non-thermally conductive Bay Blend in this application. The other components, major components that we designed in our materials are the housings. You can see here in the left, the upper and lower housing. Those were tried in several different materials, but we're going to focus mainly again on Bay Blend FR3040 EV. And that is a very common workhorse material, but depending on the properties that you actually need for the application, you could look at another grade like Bay Blend FR3080 EV, or if you need some higher modulus, Bay Blend FR3060 EV, which is a 15% glass reinforced flame retardant material. So let's talk about some of the tests that were done. We wanted to prove out that the materials, especially in this case, the housing, which is going to see the brunt of any type of mechanical loading, could be made from Bayblend FR3040 EV and meet expected performance requirements. We chose to look at a test that is probably the most universal test you can look for in batteries. It's the UN 38.3 Transportation of Dangerous Goods standard. So any battery or pack that's shipped anywhere in the world needs to meet that requirement. And within that requirement, there are 4 mechanical tests that we chose to look at to compare our materials. That would be the thermal test, a vibration test, mechanical shock, and then the mechanical crush test. So running those tests on these packs with the Bayblend material, we found that meeting all of those requirements, the materials were able to pass the requirements and were undamaged during the testing. So the test itself requires that you do not have anything open up in the pack. You are not able to access live elements. And it also specifies that there is not catastrophic failure. So in both those criteria, we met them in all of these tests and were able to pass. So we have good confidence that if a component is designed from the Bayblend FR3040 EV, it can meet the requirements and pass these tests. So the other performance is the thermal performance of the pack, and that's also critical. And what we did in this case was wired up packs with live cells. These were Samsung cells. We ran charge and discharge cycles. We ran 1C and C/2 charge and discharge cycles. We wired up the packs with 46 thermocouples. There were 45 live thermocouples and then 1 thermocouple reading ambient. And we went through all of the data looking for how the 2 materials, a thermally conductive and a non-thermally conductive material, performed and if we saw any benefit. And if you remember, most batteries do not like temperatures above approximately 60 degrees Celsius. They start to have issues. So temperature control in a pack, I don't think I need to explain, is pretty critical. And the net result was, over the charge discharge cycles that we ran, we saw a 3.1 degrees C cooler operating temperature with the Macrolon TC grades versus the non-thermally conductive grades. So you do see a performance improvement there from the thermally conductive material. Is that significant? Well, if you look at different criteria, and there's a lot of different ways of judging whether or not a thermal performance is good or bad. But one of them says that you lose cell life, you lose half your cell life for every 9 degrees C above ambient that the pack operates. So if you use that as a criteria, 3 degrees out of every 9 degrees is a pretty significant number. So dropping the overall operating temperature by 3 degrees Celsius can influence the overall cell life, overall pack life. Another key criteria is delta T across the pack. And we also took a look at that and found that with the TC materials, we were able to achieve a delta T across the pack of 3 degrees Celsius or less. So most people, the criteria is 5 degrees or less. So when you compare the results of the Bayblend material, which is non-thermally conductive, that was about 4.2 degrees Celsius. So it still meets that typical 5-degree requirement, but the TC material did outperform the non-thermally conductive material and gave us a 1.2 degrees C lower delta T of about 3 degrees Celsius across the pack. So the benefits from the thermally conductive material are there. You can see them in this particular pack. And of course, the degree to which they can help or the degree to which they affect the overall performance is going to be a factor of the design and how any particular pack is put together. So along those lines, we have the ability to do simulations to be able to take a look at designs before we choose materials to see how much benefit in your particular design the thermally conductive materials will be. So with that, I also want to add that we have the materials, the experience, and the tools to help you meet your needs for battery applications. And I want to thank you for your attention.
All right. Well, thank you very much to Nick, Matt, and Terry for that great information that you shared with everyone today. We did get a couple of questions in that I'd like to put to you guys that came from the audience. Nick, this one came during when you were talking about charging stations, and it says, do these applications require a flame and smoke spread rating due to surface area or just UL 94 rating? I believe the UL rating is 705 for the building.
Well, that's a good question. A lot of the stuff I've been working on or the customers have asked for just UL 94 for that. Now, to your point, if they're put against a wall or plenum space, we've seen UL 2043, which is a smoke and heat spread as well. But our customers are asking us, sometimes we need the UL 94. Maybe they have to do the final parts test with that. We can help with that, but typically, for us, if we don't have the final part, just like UL 2043, if we don't have the final part, the geometry, all that can have an effect. So we're being asked UL 94, but they may have additional testing that they're passing, but because we're providing the correct grade, they're passing their test. But that it's a good question though. If there's anything more that they need to ask from us, I'd have to look deeper into it.
Okay, thank you. And then this, I'm not sure who this goes to, but we probably got time for one more question, maybe two. But this one kind of came up a couple different sections. It was, I'm unsure of how to design certain features, and does Covestro design battery parts? And how can Covestro help?
Well, I can take that. So we are well versed in plastic part design. So if you're struggling with plastic parts and you're in our materials, we can certainly help you with that. We're not a design house, so we don't design bottom up parts for customers. But certainly, if you're working on a design, you're looking at our materials for the design, we'd be happy to sit down with you, go through the designs, and give you recommendations on how we would like to see it done in our materials, or how components designed in our materials. So we definitely provide that type of support.
All right, thanks, Terry. One more from the audience, real quick here, and then we'll wrap it up. Do you have grades that can be used for liquid cooling of batteries?
Yeah, so the main grade for the liquid cooling of batteries is the FR 6020 grade. And we choose that grade because of its chemical resistance to most of the coolants that are utilized. There are other grades such as, I think it's 4065 EV, that we use and manufacture overseas at some of our other manufacturing facilities. So, there's other grades that we could import into the US. But to avoid that, we've really been going toward the FR 6020 lately because we find it has good suitability for the liquid cooling systems.
Okay. Thank you, Matt. Well, with that, I think that's brings our presentation and webinar to an end. We really appreciate everybody joining us today. And just to let you know that since you registered for this, we will send you a copy of the presentation, as well as a copy of a link so that you can see the recording as well, should you want to, again, in the future. So on behalf of Covestro, this is Robert Nelson with AMCO Polymers, Bruce Serafin, and we just appreciate being with us today, and have a good afternoon. Thank you.